Hi, this is Ms. Park. I'm going to take you through a little bit of a review of grade 9 and 10 math, and I'm going to start by showing you how to get into this product called Google Jamboard. So from your Google screen, your browser, Google Chrome, or inside your Google Drive, just look for these three dots on the right-hand side. Click on the three dots, and then you have here all your Google apps. Scroll down until you see this big J for Jamboard. Okay, now I've got lots of Jamboards that I've done with lots of different people. I'm going to open a new one and create a new one, and I'm going to give it a name. So I'm going to give this name Review of 9 and 10 Math. Okay, and Jamboard is it's an electronic whiteboard, and you can share it with other people. So you can open one and share it with someone else, and then what happens is whoever it's shared with, they can all write on it at the same time. You have a bunch of controls here on the left-hand side. So this is a pen tool. You can change the color of the pen. You can change the thickness. This is an eraser. This is a pointer tool, a selection tool. This is called sticky note. So you can, in the sticky note, you can type a message and you can save it. You can change the colors of the sticky notes, okay, and it saves it there. You can import an image. Okay, so whatever you like, you can just drag an image into here. This is I'm going to cancel out of there. This is drawing a circle tool. If you want to draw a nice circle or oval, you put it in there. There is a text box. So I can open a text box and I can actually type here. So I can type things in there. And let's see. And this is a laser tool. So if you want to highlight something that's been written, you can highlight it and it will go away by itself in a second. So I'm going to use the pen tool, and what I'm doing is I'm using actually a tablet and a stylus to draw with. If you have some kind of touch screen, you can use your finger or a stylus. And if you don't, it's okay. You can take a picture of your work and stick it in, or you can just use the sticky note feature or the text box, depending on what you need to do. So I'm going to choose the pen tool. I'm going to choose a skinny one, and I guess I'm going to go black. And I'm going to start showing you now the review. You'll notice as I go through that there are pages to this Jamboard. So I'm right now on page 1, okay, but I will continue going to other pages. All right, so ready? Okay, sit back. Here's a review of grade 9 and 10 math in not too long, certainly not 2 years worth, okay, but we'll get it done real quick. All right, so I'm going to start with a concept called rectangles. Okay, now everybody knows what a rectangle is. You learned this in elementary school. I'm going to create a rectangle that has a width of 1 unit and a length of 3 units. Okay, 1 and 3. And then I'm going to create another one with the same shape. Okay, so exactly the same shape, but you can see that it's bigger. And this one is going to be a width of 2 and length of what? What does the length have to be in order for this rectangle to be the exact same shape as this one, but larger? So what I'll do is I'll say, well, if I'm going to make the width twice the size, I should make the length twice the size. And even though I'm drawing this not in the nicest way, these two rectangles have the same shape. And I can make an even bigger one by tripling the width and tripling the length. Then I can make an even bigger one. Now notice if I made one that was like a 2 by 4, that would not have the same shape as all the others. Okay, and so what do we call shapes that are the same shape, the figures that are the same shapes but different size? Okay, we call them similar figures. So these are called similar rectangles. Okay, and the reason I'm writing this in blue is every time we're going to cover a concept, I'm going to write that name of that concept in blue. Now, the similar rectangles are not really something that you learned as a topic, but it's just a matter of a shape that I picked. I just happened to pick an easy shape like a rectangle. To get from one rectangle to the next, I am going to multiply all the sides by some number. So that number that I'm multiplying it by is called a scale factor. So that would be times 2. From the first one to the third one would be, oops, okay, I'm going to use my eraser. Made a mistake here. Oops, that's not an eraser. Okay, let's get rid of this, clean that up. Okay, back to the pen. Okay, so from the first one to the third one, I'm going to go times 3. So those numbers that I'm multiplying by, I'm multiplying the side lengths by each time, they're called the scale factor. Scale factor, okay? And we know that the rectangles are going to be the same shape if the ratio of their width to length is going to be the same. So 1 to 3, 2 to 6, 3 to 9, that's the same ratio. So that's your concept of ratio. Okay, so that's the first concept. So what I'm going to do, I'm going to go to the next Jamboard frame. And so you'll see now it says there's 2 of 2. I'm going to go back to my black pen and I'm going to show you something else. All right. Now suppose I take those rectangles, the ones I'm just going to draw one of them. That's a 1 to 3 ratio. And suppose I want to draw them on a Cartesian plane. Okay, so let's say this is my width and this is my length, right? So when the width is 1, I will have a rectangle that is this big, that'll have a height of or length of 3. So that will be 3. Okay, and when the width is 2, I will have a rectangle that has a length of 6. So those are the rectangles that I drew on the first frame. And when the width is 3, I will have this, okay, and so on. What happens when I connect these points here in the quarters is that these points, if you believe me, because I'm drawing wobbly, will create a straight line. Okay, and that's because if I made a table of values out of the width and length of these rectangles that are of ratio 1 to 3, then when the width is 1, the length is 3. When the width is 2, the length is 6. When the width is 3, the length is 9. I can keep going, dot, dot, dot. When the width is 5, the length is 15, and so on. Those points, when plotted on a Cartesian plane, suppose they were x and y, right? Suppose it was like this, x and y. Then those are the points 1, 3, 2, 6, and 3, 9. And those points, and 5, 15, which is way up here, and those points will join to make a straight line. All right, so we have now looked at, using the similar rectangles, now we have looked at the concept of plotting points. And we've also looked at a linear relation, because when you connect those dots, you can you're going to get a straight line. Okay. Now notice that the very first point here is 1, 3. There's no other points to the left of this 1, 3, and really there could be. I could have a half and 1.5, right? As long as the ratio is 1 to 3. And if I had a width of 0, then the length would be 0, which means that's not even a rectangle, right? That's just like nothing. But we can't have anything negative here because we can't have negative length. So really what we've done is it's a linear relation, and we've also drawn it in context. Context means it has meaning. So that if this line was actually to continue, if we weren't talking about rectangles, we're just talking about table of values and just kind of repeat the pattern, it would continue on forever here too. It just doesn't make sense because it's rectangles, right? So the context means that there's not going to ever be points on here that are less than 0. Okay, so that's the context. Now the next thing we did, and we did this last year, it's a grade 9, or sorry, 2 years ago, it's a grade 9 thing, is come up with a relationship between length and width, or between x and y. So if I wanted to write an equation, some kind of relationship between length and width, I could say, well, to get the length, I would take the width and multiply by 3, like that. So that's their relationship. And if I talk about x and y instead of length and width, then the equation of this line is y equals 3x. And so now I have another concept, which is equation of a line. Okay, and you can see that as we rise 3, we run 1, right? We rise 3, run 1. So that is the rise and the run, which when you rise 3 and run 1, the ratio 3 over 1 is the slope of the line. And the equation of the line is y equals mx plus b. You can see the slope is 3. It's 3 over 1. There is no b, which means that the b value is 0. That's the y-intercept, and we saw that the y-intercept is 0 because when the width is 0, the length will also be 0. Okay, and vice versa. So rise, run, slope, and y-intercept, and equation of the line is y equals mx plus b. Okay, so hopefully that's okay so far. I'm going to move on to the next frame. I'm going to go back to my black pen. Again, I'm going to take my similar rectangles, so my rectangles that are in the ratio 1 to 3. And this time I'm going to make a table of values where I'm going to compare the width to the area. Okay, so when the width is 1, we know the ratio is 1 to 3, so the length is 3. So what's the area is 1 times 3, which is 3. And when the width is 2, the length is 6. So the area is 2 times 6, which is 12. And when the width is 3, the length is 9. So the area is 3 times 9, 27, and so on. I think I had a 5. So when the width is 5, the length is 15, and so the area is 5 times 15, which is 75. Well, now when I plot these points, I'm going to have 1, 3. So again, this is very rough. This is width, and this is area. Okay, I'm going to have 1 and 3, and then I'm going to have 2 and 12. And then I'm going to have 3 and 27, which is very high, and then 75 is very high. And of course, I'm not drawing this properly, but if I did, if I plotted it into Desmos or graphing software, I would see that this is actually a curve. And so I'm going to change color, and I'm going to write down the concept. The concept is that this is a non-linear relationship. Okay, and what else can we do here? We can try to figure out what kind of shape this is. Well, let's look at what the equation could be. Because if the area, we know area is length times width, and if the length is always going to be 3 times the width in our example, then the area is really 3w squared. And if I looked at this as x and y, and so like this is x and this is y, then my equation is y equals 3x squared. And hopefully you recognize this from now grade 10, because in grade 10, we learned about a certain type of relationship that has x squared in its equation, and that relationship is called a quadratic relation. So quadratic relation okay, and the graph of a quadratic relation is called a parabola. Okay, and other things we learned about it is, well, 3x squared, we can actually write 3x squared in vertex form. So you may recall vertex form of the parabola is y equals a times x minus h squared plus k. So this is from grade 10, okay? And y equals 3x squared, it's like saying y equals 3x minus 0 squared plus 0. This is equivalent to 3x squared. You'll see if you expand this out, you just get 3x squared. And this 0 and this 0, the hk, give you the vertex, which means that the vertex of this one is 0, 0. So that means that if I extended this, I'd get to 0, 0, and then I'd have a mirror on the other side. But of course, it doesn't make sense to have this negative side because you'll never have a rectangle with a negative width. right? You can go right up to the 0, but at the 0, you won't have a rectangle at all, so that 0 is not included, and the rest is negative, which is not included. Okay. Another thing I'll just throw in there, why not, since we're here, is factored form of the parabola. This is also from grade 10. And factored form looks like this: y equals ax minus s, x minus t. And the s and the t, I'll remind you, are the x-intercepts. Well, what are the x-intercepts of this parabola if it was to continue all the way and not have any parts missing? It would be 0 and 0. So in the case of y equals 3x squared, this is y equals 3, x minus 0, x minus 0. If you expand that out, you'll get 3x squared. So the x-intercept, or the zeros of the parabola, there's only one. Okay, the first one, usually there's two if it's going to cross the x-axis in two places. In this case, one of them is 0, the other one is also 0. So there's only one, which is 0. You know what? I'm not going to write that. I'm going to write it like this. There's only one x-intercept, so I'm going to write it in the singular. So x-intercept is 0. There's only one. Okay, so what have we done now on 3 frames of the Jamboard is that we have really taken the concept of similar rectangles and reviewed linear relationships and quadratic relationships, and we even reviewed the forms of the quadratic relationships that are useful. There is another one called standard form, little less useful. These are the useful ones. Okay, I'm going to show you one more thing, and that'll be the end of our review for now. If I remember that one where you know what, I'll go to the first frame. Okay, no, it was the second frame. So remember this, when I stacked one on top of the other like that? I'm going to do the same thing on the 4th frame. I'm going to stack them. Let's do this, clear the frame. I'm going to stack them like this. So here's the 1 by 3. I'm going to have it stand up, and then I'm going to put the other one on top. Okay, so this is similar to the when I did it on the Cartesian plane. So this is a 2 by 6, and then this one is going to be the 3 by 9, and so on. Okay, so that's 3. This is 6. This whole thing is 9, and so on. Now what I'll do, and change the pen, I'm going to take a line and draw it right through these corners. Let's see if I can do that better. So I'm going to Control Z to undo, and let's see if I can do a better job of that. Let's pretend this is a straight line. Okay, good enough. And what I've actually created is these right angle triangles. So if you ignore this part up here, you'll see that what I've created is right angle triangles. And so these right angle triangles, where that's a 1 and that's a 3 and so on, I'm just going to redraw it a little bit so that I don't have all the stuff on it. They look like this. And this is a 1 by 3, this is a 2 by 6, this is a 3 by 9. And you can see that the ratios of the sides are always 1 to 3, 1 to 3, 1 to 3. So these ones are called similar triangles. And you have to imagine that these triangles are 3 separate triangles. I'm drawing them one on top of the other because it looks like this, but really they are 3 separate triangles, a 1 by 3, and look, I'm drawing them the same size, but you get the idea, a 2 by 6, a 3 by 9. These are different triangles and they're similar. Now, what did we learn about similar triangles in grade 10? We said that for any right angle triangle, we can write a ratio for the sides. So if the 3 over 1, if I go, let me get black. If I call this an angle and give the angle a letter, then we have names for the ratios of these sides. So this is a 3 and this is a 1. Does anyone remember what you call this opposite side divided by this adjacent side? So that is called the tangent ratio. So the tangent of A is equal to the opposite over the adjacent. So in our case, it's 3 over 1, which is 3. And the tan of A, if A was here or here or here, is always going to be 3, because always the ratio of those sides. Now, that is, we call that trigonometry. I'm going to write it here. And we also had an acronym, SOHCAHTOA. And the S and the C were sine and cosine. So sine and cosine involve the hypotenuse of this triangle. So how did we calculate the hypotenuse of this triangle here? So then that's where we said this is a right angle triangle. So we have a relationship called the Pythagorean theorem, which is little a squared plus little b squared equals c squared. But little a squared doesn't match up with the letter A where I've put it, but it doesn't matter. The relationship is the same. It's the short side plus the other short side equals the long side. So squared, right? The squares of the short sides added together equals the square of the long side. So 1 squared plus 3 squared is 10. That's its question mark squared. So question mark is the square root of 10. So sine of A is the opposite over the hypotenuse. Okay, so sine is opposite over hypotenuse. So that's going to be 3 over root 10. And cosine of A is adjacent over hypotenuse. Adjacent over hypotenuse, 1 over root 10. And there you have it. So now those similar rectangles took us through linear relations, quadratic relations, similar triangles, and trigonometry. Stay tuned for part 2, where I'm going to blow your mind. And similar, so rectangles are going to be used for all kinds of algebra, and that is in the upcoming video. Thanks for watching, and we'll see you soon.